We are in the middle of one of the most active seismic stretches the planet has seen in a while, and at the same time, the sun is stirring. Two things are happening at once, and today we're going to walk through both of them plainly with the real numbers, and without pretending we know more than we do. Let's start with the earthquakes, because this is the part that is verifiable, and it is genuinely a lot. On August 10th, a magnitude 7.4 earthquake struck Colombia. 4 days later, on August 14th, a magnitude 7.7 struck Indonesia. 2 days after that, a magnitude 6.9 struck Indonesia again. That is 3 major earthquakes, all above magnitude 6.9, in the span of about a week, on 2 different continents. When you get a CL, used to like this, seismologists call periods like this a global seismic burst. Stretches where high magnitude activity clusters together in time, even across completely different fault systems on opposite sides of the planet. These bursts don't have a single agreed upon cause. Sometimes they're coincidence. Sometimes there's genuine stress transfer between major fault systems thousands of miles apart, though the mechanisms for that, over such distances, are still debated among seismologists. What's not in question is the raw activity. This has been an intense week. Indonesia in particular has been rattled hard. In the 7 days following the magnitude 7.7, there have been 63 aftershocks of magnitude 4.5 or greater. 27 of those reached magnitude 5 or higher. 1 reached 6.1. The fault rupture spread across a wide stretch of the region. And aftershock sequences like this are completely normal after a quake this large. Big main shocks redistribute stress along the fault, and that stress has to release somewhere, which is exactly what we're watching happen in real time. Separately, a magnitude 5.8 struck near Kamchatka, and a magnitude 6.1 was recorded near Vanuatu. None of these are connected by a known physical mechanism to each other, but taken together, it paints a picture of a planet that has been unusually active seismically over the past 2 weeks. Statistically, magnitude 8+ earthquakes happen globally roughly once a year on average, and it's been over a year since the last one, a magnitude 8.8. To be clear, that's not a countdown or a weird-do mechanism in any predictive sense. Earthquakes don't work on a schedule and a gap, since the last big one doesn't make the next one more likely on any given day. It's simply useful context for how rare and how significant an E+ event actually is, and why seismologists take any cluster of large earthquakes seriously enough to watch closely, even without being able to predict exactly what comes next. So that's the seismic side. Now here's the volcanic side, because it hasn't been quiet either. Klyuchevskoy volcano had a large eruption, sending an ash cloud roughly 10,000 meters into the sky, and that eruption occurred almost exactly 24 hours before the magnitude 5.8 near Kei-Aviti, including some new flank eruptions. And over in Hawaii, Kauawea has now had 53 fountaining episodes since its eruptive sequence began in December 2024, the fastest pace of lava fountaining episodes this volcano has produced in the modern monitoring record. Now here's where the sun comes into the picture, and I want to be upfront with you about exactly what is fact and what is a working hypothesis, because those are 2 different things, and you deserve to know which is which. The sun has had a noticeable uptick in activity. Over the past several days, we've seen new sunspot growth, a jump from very low background X-ray flux up to more frequent C-class solar flares, a 4.1 C-class flare on August 14th, and an 8.2 C-class flare on August 16th. To put that in perspective, C-class flares are relatively minor on the solar flare scale, well below the M-class and X-class flares that this solar cycle has already produced and will likely produce again. But going from a quiet baseline to consistent C-class activity does mean Earth's ionosphere has become more charged and more active than it was a week ago. There are also 2 coronal holes in the sun right now, regions where the sun's magnetic field opens up and allows solar wind to stream out faster than normal. These aren't connected into one giant equatorial hole, which actually limits how strong their combined effect on EO-RAF is likely to be, according to the geomagnetic forecasting used to track this. As of today, the solar wind has strengthened to about 10 nanotesla, roughly twice the normal field strength, and the vertical component of that phi, LD, has flipped negative, which means it's coupling more efficiently with Earth's own magnetic field. Solar wind velocity is still relatively modest, at around 355 kilometers per second. Based on this, a G1 and possibly a G2 geomagnetic storm is plausible over the next couple of days. Minor to moderate storming, not an extreme event. Here's the important distinction. There is a hypothesis, discussed in some space weather and earthquake monitoring circles, that coronal holes and geomagnetic disturbances can influence or help trigger seismic activity. The idea being that changes in Earth's electromagnetic environment add stress to already loaded faults. This is not settled science. Mainstream seismology, including the USGS, does not currently recognize a reliable predictive causal link between solar activity and earthquake triggering at these magnitudes. There is a body of research looking at correlations between ionospheric disturbances and earthquake activity, and that's a genuinely active area of study. But active area of study is very different from established mechanisms. So when you hear this connection floated as an explanation for why earthquakes are clustering right now, treat it as an open question being explored, not as a confirmed cause. We'll flag it every time it comes up, because you should get to decide what you believe once you know what's actually been demonstrated and what hasn't. Now let's talk about Hawaii specifically, because a lot has happened there in the last few days. And it's not just earthquakes. Hurricane Lala made an almost direct hit on the Hawaiian Islands as a Category 1 storm. The eye wall didn't technically make landfall. The elevation of the Big Island tends to steer storms like this, but this was as close to a direct impact as you can get. And the rainfall totals were staggering. Some locations on the Big Island received over 40 inches of rain. Many spots exceeded 20 inches. Wind gusts at the Mauna Kea summit reportedly reached 140 miles per hour, with other locations seeing gusts beyond 70 miles per hour. Kona reportedly saw gusts near 80 miles per hour. The damage has been serious. Roads and bridges were washed out. Some homes were reportedly washed away. Areas near Pahala, on the southeast side of the Big Island, were hit hard. And that location matters because Pahala sits above a magma sill complex connecting Mauna Loa and Kalauea at depths of roughly 30 to 50 kilometers, an area that regularly produces earthquake swarms tied to that deep magma system. Power outages hit much of the Big Island during the storm, and some communities were cut off entirely as roads eroded out. Even Mauna Kea's summit reportedly saw snowfall during the storm, unusual for August, tied to the unusually cold air brought in with the system. So now the question everyone in the volcano-watching community is asking, does dumping this much water into Hawaii's groundwater system change anything at Kalauea? Here's what the actual tilt data shows, and this part is real, measured ground deformation, not speculation. Kalauea's summit tilt record over the past year has generally followed the expected pattern for this eruption. Inflation as magma recharges the system, then deflation as an episode releases pressure over and over. But the recent data shows something a little different. A longer, deeper period of deflation than typical, followed by a sudden shift to rapid inflation that coincided with a magnitude 5.2 earthquake at Kamaehua Kanaloa, the seamount off the southeast coast of the Big Island. Episode 53 followed shortly after. Since then, the tilt data has shown another period of deflation, along with increased noise in the readings caused by Hurricane Lala's rainfall interference with the instruments. Heavy rain can introduce erratic signal into tilt meters that has nothing to do with actual ground movement, which is exactly why scientists cross-check tilt data against seismic and gas data rather than relying on any single instrument. At Keizalauea's East Rift Zone specifically, the deformation trend had been trending downward, deflating, for roughly 3 months. Following that magnitude, 5.2 earthquake at the seamount, there's been a small uptick in inflating. At the East Rift Zone, it's not yet clear whether this is a meaningful trend reversal or a short-term blip before the longer deflation trend resumes. The East Rift Zone matters historically because it was the source of the major 2018 eruption and the destruction that came with it, so any shift in its behavior, however small, is something scientists are watching. As for when Kalauea's next episode might occur, one pattern some observers have noted is that the last several episodes have loosely lined up with the lunar cycle, occurring closer to full moons. That's an informal observational pattern floated by watchers of the eruption, not a scientifically established triggering mechanism, and the volcano's actual USGS forecasting is based on the tilt, seismic, and gas data described above, not lunar timing. If you're looking for an actual forecast window for episode 54, the official, word remains the same as it's been throughout this eruption. Reinflation suggests another episode is likely, but a precise timing window requires more data, and USGS Hawaiian Volcano Observatory updates are the most reliable place to track that day by day. Let's slow down for a second and talk about how scientists actually monitor all of this, because it explains why some of these numbers get revised, why forecasts stay vague on timing, and why we don't know yet is often the most honest answer available. Earthquake monitoring relies on global networks of seismometers that detect ground motion and triangulate the location, depth, and magnitude of a rupture within minutes. Early magnitude estimates are often revised up or down slightly. As more stations report in, that's normal and doesn't mean anything was wrong with the initial read. It means the picture is getting sharper. Aftershock sequences are tracked the same way, station by station, and the numbers we quoted for Indonesia, 63 aftershocks above magnitude 4.5, 27 above magnitude 5, reflect a live count that will keep climbing as the sequence continues to unwind over the coming days and weeks. Aftershock sequences typically follow a well-documented decay pattern. meaning the frequency of aftershocks drops off over time, though the timeline can stretch from days to months depending on the size of the main shock. Volcanic monitoring works differently, and we touched on part of this with Kilauea's tilt data, but it's worth walking through fully because it's the clearest window we have into what's happening undergrow. Tilt meters measure the ground physically swelling or sinking as magma moves in and out of a shallow reservoir. Inflation typically precedes an eruptive episode. Deflation typically follows one. Seismometers at volcanoes also pick up volcanic tremor, a distinct continuous signal caused by fluid and gas moving through bare ground conduits separate from discrete earthquakes. Gas sensors track sulfur dioxide output because a magma body releases more gas as it nears the surface and depressurizes. And satellite radar plus aerial photography lets scientists see physical changes to a volcano's summit or vents that ground instruments can't directly measure, confirming what the other instruments are suggesting. All four of these data streams get cross-checked against each other before scientists issue any kind of forecast, which is exactly why weather events like Hurricane Lala complicate things. Heavy rain can physically distort tilt meter readings, sometimes for a day or more after the ring, and stops, introducing noise that looks like ground movement but isn't. That's part of why the tilt data around Kilauea over the past several days has been harder to interpret cleanly. The instruments themselves needed time to settle back to a reliable baseline after the storm passed through. Now for the solar side of the monitoring picture. Solar observation relies heavily on space-based telescopes because a lot of the radiation scientists track, including the soft X-ray flux used to classify flares, gets absorbed by Earth's upper atmosphere before it ever reaches the ground. That's why flare classification, coronal hole mapping, and coronal mass ejection tracking all depend on satellites positioned to watch the sun continuously, rather than ground-based telescopes. TITAS-T. The X-ray flux scale used to classify flares runs from A and B class at the low end, up through C, M, and X class at the high end, with each letter representing roughly a 10-fold increase in intensity. The activity we've described this week, a run of CCLS flares after a period of quiet B-class background levels, represents a real, measurable increase in solar output, but it remains well below the M-class and X-class flares this solar cycle has already produced at its peak, and likely will again before the cycle winds down. Geomagnetic storm forecasting, meanwhile, is built around a different set of measurements: solar wind speed, particle density, and the orientation of the interplanetary magnetic field, especially its vertical component. When that vertical component points opposite to Earth's own magnetic field, as it currently is, the coupling between solar wind and Earth's magnetosphere becomes more efficient, which is what raises the odds of a geomagnetic storm. Storm intensity is measured on the G scale, from G1, minor, up to G5, extreme. Based on current solar wind readings, a G1 or possibly G2 storm is a reasonable expectation for the next couple of days. Not a severe event, but enough to be worth tracking, particularly for anyone monitoring aurora visibility at higher latitudes or systems sensitive to geomagnetic disturbance. Let's return to the regional picture in Hawaii, because the recovery situation there deserves more than a passing mention. The damage from Hurricane Lala has been concentrated most heavily on the eastern side of the Big Island, where rainfall totals were highest. Areas like Lapahoho and Nahuku recorded totals well above 35 inches over just a few days. By contrast, the western side of the island, Aiain, the rain shadow of Mauna Loa and Mauna Kea, saw far less. In some locations, there remained in drought conditions even as the east side flooded. A reminder of just how dramatically elevation and geography shape rainfall distribution assess these islands. Rainbow Falls, an 80-foot waterfall on the east side, was running at a dramatically elevated discharge as a result of the runoff, a visual marker of just how much water the island was processing in a short window. The other islands weren't spared either. Maui's upper slopes saw totals exceeding 20 inches. Kauai, which already ranks among the wettest places on Earth in a typical year, saw significant totals as well. Oahu recorded lower but still notable rainfall, with over 13 inches at some upper elevation sites. The infrastructure damage from this kind of rainfall is exactly cut off as access roads eroded away entirely. Solar and battery systems, which helped some households. There's also a secondary hazard worth flagging directly. Slopes can fail well after a storm passes. Sometimes where does that leave us right now today? On the ground, truth side, 3 major earthquakes fall on Hawaii and caused real, serious damage. On the space weather side, real measurable solar activity not verified. Any causal link between that IY right now that cites the honest, full picture as of right now, wondering what to actually watch for over the next few days. In the coming days would be consistent with a sequence this size. The practical marker is the tilt data at magnetic side. If you're the type who likes track, each of those is real and worth